Right? So, I mean, you get the idea. And this is all about, maybe one can at least already at this example see, when we say high frequencies, those are always required if you want to have sharp features. Right? The line here in the middle, that's a straight line without much features. So this is well approximated already by the zeroth order sine wave, the first one. But if you want to describe that sharp feature here, that edge of the sawtooth, the higher the frequencies are of your sine waves, the better you are in approximating those. Okay? So narrow features require high spatial temporal frequencies. And in all this analysis, actually, it doesn't matter whether it's spatial, you approximate some structure, or whether it's temporal. You could also think that this might be some signal that you measure in the lab where time is on this axis. It's equivalent. Okay, so that was the Fourier series with the sum here, but that's usually not so convenient and hard to compute. What you would like to do is to actually have an integral to solve. And we can write it in a more sophisticated form with an integral and get rid of the sines and cosine waves. But in order to get rid of them, we need a formalism that has been developed by Leonhard Euler. And I'm just showing you this here as a reference. If you've heard it before, it's fine. If you haven't heard it before, you will not understand it from that slide or from an explanation in 5 minutes. So that's why I put this in parentheses. This is just for your reference. There is a lot more behind that, of course. But in principle, what Euler did was to display, to introduce this complex number here, and then define that as a combination of cosine and sine waves, geometrical sine components. Here is a geometrical representation on the circle. And so he introduced this exponent here, I 2 pi theta, theta is this angle, as the sum of cosine term plus I times theta. So, and with that formalism here, we can rewrite this Fourier series in terms of these basic waves that are given by Euler's formula. So, and this is the fundamental definition of a Fourier transform. You have two functions that are called Fourier pairs, or this one is the Fourier transform of this function f of x. And just not to get confused, we have the one that we use as a starting point with a small f of x, and then the Fourier transform of that we use a capital F and have another parameter s, but they're corresponding. And then we have the integral then over this function from minus infinity to plus infinity, or in reality, when you compute that, of course, it's from over a large interval. Definitely need a large interval, but not practically never infinity, times this exponential function here that's given by Euler's formula. But again, remember that in principle, this term here only represents the combined sine and cosine waves. Okay? Also, we use x here as a simple variable, but the whole thing would also work in 2 dimensions or in 3 dimensions. And this is also, you can invert it. You can solve for f of x if you have this function, and then f of x is just the reciprocal function here. Okay, that's the basic idea of Fourier transforms. You measure f of x, you do this computation, and you get this as the Fourier transform. Yeah? And now,
and yes, play here the role of frequency. This is something
yes,
related to
frequency. Yes. So, okay, maybe let me come back to my a stupid example of the trees outside. Okay? So let's say I'm looking at a one-dimensional forest, right? I have the tree. Oh, okay, these are all trees. I have the trees here. I don't know. Okay, so this is X, right? We measure our forest in X, where X is maybe meters or whatever from tree to tree. Okay, now we do the Fourier transform. Yeah, this is f of x. Now we do the Fourier transform and we get f of s. And that would tell us, okay, we would then know, after this Fourier transform, essentially what frequencies s are most common. So we can already stand here. The frequencies are spatial frequencies, like distances. Right? So if I look at this tree here, I would say this is a very common frequency, right? You can see here, here, and here, and here. So at some frequency that corresponds to whatever, say 3 meters distance between the trees, I would get a peak here. Yeah? But I also have some trees that are, well, they grew together, so they're some high frequencies. So high frequencies here. Okay, I have another peak here. And there are some in between here, but there's not much in between those distances and those, so they're fairly zero, pretty close to zero. So I've just computed my Fourier transform of the forest tree distribution. Okay? Now, the Fourier transform has many properties, and I'm not going to go into that in detail. That's also again why I put this into parentheses here. And as you know, if it's in parentheses, I'm not going to ask in the test. But keep this as a reference in case you need to know more about it. So all kinds of how two Fourier transforms they behave, and they're linear, how they translate in frequency space. And so we don't need to worry about this at this point. But there is one property that is very relevant when we discuss telescopes. Mathematically, this property is called similarity. And what it describes is the following. We have a function f of x, that's our sort of function. And let's say this is a box function. Okay, a box. And the Fourier transform of that box is illustrated here. So mathematically, we'll see how that's actually a sinc function, but it doesn't matter at this point. If you make the Fourier transform of that, the function looks like this. Okay. Now we double the width of our box. So we just have, instead of f of x, we say we just broaden the function here. Well, if we double it, obviously a is 2. And then the Fourier transform will also change its shape. Namely, then it will become 1 over a, or in this case 1 over 2, times the original one. So if we then stretch the source function, we will make the Fourier transform here. And this is something you may say, yeah, why? But this is very important, and we'll see later why. Because maybe someone already knows what this will be. Maybe someone has a guess. Do you have any idea what? This is a course on observing techniques, right? What this box may eventually represent.
A signal?
Sorry?
A signal? Maybe a signal?
No, the signal would be here. This box will become our telescope, essentially. There's no mirror here, and then you have a telescope mirror from here to here, and then you have that's our telescope. And this is how the star will look like. And then you take a bigger telescope, and the star becomes sharper. So this is the telescope, this is the Fourier transform of Fourier. So optics, any optical system does lots of Fourier transforms all the time. Okay, let me show you some other examples, just to illustrate the idea. This is what we just discussed. And since we said you can transform back and forth, it doesn't actually matter what you say, what f of x is and what capital F s is. It's interchangeable at some point. Well, this is close to a Gauss function, and Fourier transform of a Gauss function is a Gauss function. And the only one I would like to highlight here is the mathematical delta function, which is essentially a flat, has a Fourier transform over all frequencies. Or in other words, to describe a mathematical delta function, you need all frequencies to put in. Because if you put in only a finite number of frequencies, then it will not be a perfect point here in or in.
That means if you have a telescope with a infinite aperture, star will be real points.
Right. But there's practical limitations. Right? Okay, so we said that we talked about this before, but let's now do a little bit more math about this. This box function here, let's define it as x over a, where a is simply define or indicate the width of this box. So then the Fourier pairs are to that, the Fourier corresponding Fourier pair is the sinc function that we see before. Right? And the sinc function is simply the sine function of some argument divided by the argument. Okay? So with the similarity relation, we get that this the corresponding Fourier pair is this side box function, and here the sinc function. This again, just what I said before. But of course, we can generalize it and go in 2 dimensions. Now it already looks better, more like a telescope. So if we have a 2-dimensional box function, hat function, or whatever you call it, with simply where r is x squared plus y squared, now we have 2 orthogonal spatial coordinates defined in a similar way as before. Now the corresponding Fourier transform is not anymore the simple sinc function here, but it gets a bit more sophisticated when you go in 2 dimensions. And the solution to that is now this function here, and J1 is called the Bessel function. Okay, and how it looks like is illustrated here. This is a plot of a Bessel function. And I should also say that now these are now the corresponding pairs. Right? This was before our in 1 dimension. This was our rectangular box function, and then we had the sinc function. Now we have the 2-dimensional box function, and the corresponding Fourier function is given by this expression here, which includes this Bessel function. And the coordinates that are used then, I'm not consistent entirely here before we said capital F S. Now if we have two coordinates, we call the coordinates corresponding to X and Y, we call them U and V. Right, this is just some nomenclature, right? A, B, and C, and D are being used for many other things. X and Y are already at the end of the alphabet, so you pick some other two letters at the end of the alphabet, and you end up with U and V. However, this is generally done, and you may hear people working radio astronomy and interferometers in particular. They always talk about the UV plane. If someone mentions UV plane, you know already they're not working in real image space, they're working in Fourier space. So we talk about the Fourier transforms. So in Fourier space, the coordinates are generally U and V. In the image space, they're X and Y. Okay, this is another side note in brackets, because I mentioned the Bessel function here. So I thought I should at least introduce Friedrich Wilhelm Bessel as a mathematician and astronomer. And he did a lot of work on that and found solutions to the Bessel's differential equation. Those were actually, I think they were important at that time to solve all kinds of thermodynamical problems. But this is a differential equation, and he needed the solution to this equation, which had other applications in physics. The solution to these equations are cylindrical functions, meaning they have a spherical symmetry, and they're given by this term here. Now this is more complex than what we need, because you can see that the solutions there, it's an infinite series of these functions. But if you just put n to 1, then this is much simpler, and the functions are shown here. So if n is 0, then it would be a 0th-order Bessel function. You get the red line. If you have a first-order Bessel function, you get the green dotted line, and so on.
So if I would go to even higher dimensions with my Fourier transformation, would I still solve it with a Bessel function, or so what is that? Is it still kind of the same solution, or what is that?
Well, so far we're not talking about how many frequencies. This is a general mathematical solution for this Fourier transform.
Okay.
Right. So in principle, this works from 0 to infinity, so you have everything included. There may be some simplifications, but we don't worry about this yet. So far, this is general. Okay, and these Bessel functions are also known as cylinder function or cylindrical harmonics. In fact, so if you just want to learn more about this basic stuff, you can also look it up in Wikipedia. That's actually where I got this figure from. So just to give the credit to Wikipedia. And okay, now we know how this function looks like, although we don't really need to know because we're not computing it now. But now we come back. Why is this of interest to us? It is of interest because...
Sorry, it's interesting to see that J1 actually has a 0 in W equal to 0. But since we are dividing by W, it has a peak, right?
Yes.
Yes. That's because the previous talk it starts at 0.
Right. I think that's the... That's a very good point. I noticed that when I actually looked at the slides there. And I thought no one would notice. Okay. So let's say this is this represents the aperture of our telescope. Of course, it's a very simplified telescope, but then the focal plane will get this function. And we know from the similarity relation that if we increase the size of the box here, the corresponding Fourier transform will then scale with that parameter, and that means that larger telescopes will simply provide smaller point spread function. And the point spread function, that's a term you will hear many times through this course, I'm afraid. It just means, well, you start out with a point, you trace it through the optical system, and at the end you will not get a point again, but something with some structure, so the point has spread out. Right, so this is the image of the star, image through the telescope will have some structure as given by this formula, and we call that what we would, if we put a detector here in that point, then we would see a point with some spread over a certain area, and the intensity distribution is given by this term. Now remember, in this whole discussion I'm doing like what I discussed yesterday does not exist. Like there's no atmospheric scene, because if you would add atmospheric turbulence here, you would not see that structure, you would see a big scene called here. But for today, we pretend there is no atmospheric scene. Okay. I mean, we'll get back to this idea of point spread functions a couple more times. So if it's not clear yet, hopefully it will become clear when you see a few more examples. What I should point out is that we'll see later again. The star I'll get back to that after that. I just had a couple of examples because you can, of course, compute the Fourier transforms mathematically. And we've done that for a couple of telescopes. Because you will not find a single telescope that is as nice as this pupil. Most telescopes have, well, one thing that's not in here. What do most telescopes have when you look at the primary mirror? Sorry? What's the difference between here and the telescope mirror? It's curved, but it's a small curvature, even more than that actually. But yes, it's a significant difference. What? Have you seen the telescope mirror?
Yeah, the mirror, the focus.
Now there's another mirror.
Which blocks?
So pupil that the light will see from a distant star is actually not like that, but has blocking the middle, right? And then if we have telescope, well, and that is not actually okay. Now this is very basic. How does a telescope look like? We have the star here. We have the primary mirror here. In the easiest case, we put our detector here. Yeah. And so we have the starlight coming from infinity. Well, obviously I can't draw that. But let's say we have the light coming from infinity. And then it's reflected here. I mean, there's essentially you need two mirrors if you put the detector here, because if you have a mirror, then of course you have to point to the star, and that means that the light gets reflected back. So in this case, it's reflected to some point here. Now we put another mirror here that reflects the light down to our detector. Yeah? Now the result of that is, of course, that comes from the star. So if you ask the star what pupil it sees, obviously it will not see this pupil, but it will see something like this. Right? It will only see that area. Now for practical reasons, since we live on a planet with gravity, that mirror would fall down if it wouldn't be held in place by something. Right? So this is why your telescope mirror, some structure here, you have some cables going over here. Again, if you ask our star what he or she will see from the distance, it's not only that pupil, but it has the central, it's called the central obscuration, right? Obscuration. Something is obscured. And because it is of the secondary mirror, you often find then some mechanical structure here that just holds the secondary mirror. Okay, now this looks already very different. What we have computed before was this, right? And you can imagine that what we said before about spatial frequencies, or remember the sine wave approximation of our sawtooth function. Large structures result in low frequencies. Very tiny features result in high spatial frequencies. So, since this is in the pupil here, this is tiny, right? The pupil is big, so we have a few meters apart, but then we have these cables in the pupil of the telescope and the smaller structure. So we know already that this will add some higher frequencies to the image. So we expect not to get a very nice function like this one here, but what we will actually get as the Fourier transform then, our point spread function, that pupil will look a lot more ugly or more complex. In any case, you will find all kinds of artifacts and features there. And that I can show you because this was done in some computations. Again, this is, I hope you can see it and the contrast is sufficient. So if you had I mean this was done for a 39-meter telescope, surprise, surprise, but the principle works of course for any size telescope. So if this is the representing telescope pupil with the central obscuration, but it uses the assumption the mirror surface is smooth and flat, and there are no spiders, no telescope spiders like those ones hanging in here. And you get a complete spherical symmetric image of rings. Now this is in logarithmic scale.
Oh yes, I will this video because it produced.
Yes, it's better.
Yeah, I'll give you that. Okay, just to see the.
Yeah. So you see all these rings here. These rings here are essentially the wiggles here or here that mathematics predicts, or given by the Bessel zero or the Bessel function. Oh, sorry, first of all, the Bessel function. Okay, so this is the Fourier transform of this in log scale. Or in other words, this is the point spread function of a star you would get if you observe it with a telescope that pupil. Now, next we add a couple of features here of our real telescope. So now, I mean, this was done for extremely large telescope. So extremely large means even the secondary mirror here is something like 4.5 meters. Okay? That's about the size of the podium there. And that's the secondary mirror hanging high above your 39-meter primary mirror. And obviously that one, I mean there is always wind, right? That one shouldn't shake around, so you need to fix it properly. And you need a couple of these connections. And now you see this symmetry here also reflected. Before it was rotationally symmetric, right? No structure here because there's no structure here. Now you break that symmetry. You introduce the six-fold symmetry here, and you also see that in your point spread function. Now, again, keep in mind this is log scale. The problem is now, if you look at the tau scale, at the dense star cluster, all of the stars will not look like points. They will all have this structure. And you're going to be very pleased because obviously our star now has lots of planets around. But and these are exactly these, what I said before, these high frequencies that are ended by diffraction from the spiders and the intersection points here with the secondary curve. Now we can make it even uglier because have you ever seen a 39-meter mirror? One piece of mirror? Apart from the fact that you would never get it to the observatory site because it would fit on no road, in no airplane. Yeah. You have to make the mirror smaller and piece it together. Okay. So we now have a segmented pupil mirror. That means we have a pupil that's built of smaller segments, 1 meter mirrors that we put together. Now when you put it together, you always have a gap between the mirrors. Right? Gaps between the segments. And again, these gaps, with respect to the pupil and high frequencies. High spatial frequencies, and that will show as additional high frequency structure in our point spread function. I mean, this would be a great Christmas decoration. But this is what you have to deal with then. This would be the Fourier transform of that pupil. And then we put it all together again, we add the spiders, and this is the nominal point spread function of a 30-nanometer. Now, to some extent, this applies to all telescopes. It's also for diffraction limited performance of the Keck telescope, where you have segmented mirrors. Similar. If you have, of course, these are tiny structures here, and they're much fainter than the central peak. Again, in order to show that, you use logarithmic scaling. If you put this in linear scaling, you see the central peak, and you see the spiders here, but you probably will not see the end structures here. So this is mainly for illustration, and it's also, of course, in the absence of noise. So this is a pure mathematical transformation. But anyway, I think it shows the. Yes.
Do these patterns caused by, like, these patterns are caused by physical processes? Is it by just diffraction of light against the structure and self-interference, like when it's going back to the detector?
Essentially, yes.
I have noticed that the central mirror doesn't change too much the original pattern.
I'll get back to that.
Okay.
It has an effect. It actually, it's a complicated dependency. You press a lot, it makes your PSF even narrower if you have a larger central obscuration. You would, in fact, you get the best images if you would have only a telescope that's made of an outer ring. But then why do you build a thick mirror and then you throw away all the photons by putting a big central obscuration there? But yes, it has an effect. But it has an effect more on the scale of the PSF than on the structure.
But in that case, you can build a very big air telescope having the same area like a 35 meters telescope, but with a very huge diameter. Isn't that advantageous?
Yeah. Well, yeah. I I mean, sorry, I have to answer Jorgen now, so this is there were times when ESA was planning to build 100 meter telescope. Like, they were a bit over the top. Okay, 100 meters. With only, and the idea was to make it only of spherical mirrors. And so you needed thousands of spherical mirrors. And it was clear that it takes 15 years to produce all these mirrors. And so they were thinking, well, can we do some observations, even if the telescope is not complete, but just continue to put in mirrors? And so we did some calculations on how the point spread function would look like. And it was very interesting with regard to exoplanet detections, because your point spread function changes depending on the pattern, how you fill the pupil. And in many cases, of course, the problem is that, let's say you look at some star, and you find a spot here, right? And you don't know, well, I mean, one simple solution is to observe it again after half a year, and if it hasn't moved, it's probably part of the image, the telescope PSF, and it has moved, that it may be some exoplanet. But you could also get an optimized image for specific distances from your star if you fill the pupil incompletely. And there are people actually who do that with sparse aperture masking, who actually, in their instrument, put in masks that take out most of the light of the pupil. They compute, they make computations, and they say, oh, hey, let's look. We'll block that part, and we'll block that part, and that one, and then the image looks very different. And you can change those masks, and you have complete control over how your image looks like. There's a whole optical industry behind that. But in the end, they all look strange. Right? Okay.
I will turn on light again.
Yes.
Now, get to
Okay, so here's another sheet, and actually I'm not sure, maybe I will refer to some of that. These are theorems that are related or can be derived from the Fourier principles. The most important one here may be the convolution. And the convolution of two functions is essentially the integral of the product of their Fourier transforms. And on the next slide, I'll show how nature does that, actually. I don't think we have the time to go into that in detail, but I also wanted to have the most important relations here listed, so you can keep that as a reference to look it up. So this is the definition of convolution, cross-correlation, autocorrelation, power spectrum, and those two are probably way too complicated for now. But yeah, I mean, you can ask me about that, but I just wanted for completeness to add them here, because the convolution is an important one, and I'll show you one example. Let's say you have two objects, a bright and a faint star, and then the telescope does something, or well, the atmosphere does something. Well, something will happen to your object, and then the image that you observe can simply be expressed as the convolution of those two components, namely the source function, the way your original image looks like, convolved with, so not multiplied or added or so, but this is the convolution then, with this point spread function. And that point spread function that may be...
this slide doesn't appear in your copies, right?
Sorry, yeah, I added just 5 minutes of work for the lecture, sorry. Yes, so the point spread function may be something like that, or that ESF, think about the atmospheric dispersion we talked about last time. If every point will be imaged because of the atmosphere of the rainbow, that also means you could essentially convolve your original image with that rainbow function, and the resulting image is then given here meaning that every star here, this one, the brighter one here, have then the features of this one. And the interesting thing is that you can also invert them. And then it's called deconvolution. And we'll actually get back to well, not mathematically, but an application for deconvolution we'll discuss on Thursday, where we talk about telescopes and talk about the Hubble telescope. We had a big aberration there, and then people could get rid of it mathematically by these tricks using deconvolution. Okay, so what I said before, there are various ways to think about the image formation. You can say, I have a star, it sees only the finite size pupil, and so it reduces some frequencies. I mean, that's the picture that Jorge sort of referred to before. Right? If we have keep in mind, so we have the star here at infinity, and we would put a telescope. This box here is our universe. Okay? So we put a telescope as large as the universe here. Just make a lens here. Yeah? And so we image that. Well, of course, we realize that that lens should actually be around the star. Right? Because obviously, the star, that's one of the problems, the star radiates in all directions. And we wouldn't get those, so it can't be as large as the universe. But, okay, so our telescope then takes out only a small part of that information from the star. And because it is smaller than infinity, it essentially filters, again, from image to pupil, standard optics from image to pupil to image. It's always essentially a Fourier transform. Okay? So the fact that our telescope has a finite size will filter out some frequencies. And it will filter out the highest spatial frequencies, meaning the highest structural details. So when we then make an image, right, we'll get a our point of function. And of course, if we now use a smaller telescope, and the smaller telescope means we lose even more spatial frequencies. We lose even more spatial information. And then, of course, we can also form an image. But in this case, because we lost more information, we lost that information that a bigger telescope would have recorded. So our images, the star look bigger. Or what, in other words, if you wouldn't image a single star, but if you would image two of them, in the case where you have the big telescope, that's a small little star. Right? Let's say we have a double star here. So in the case of the big telescope, we had one image here and the other one here. So we would still see a double star with two peaks. But now, if we lose some information, because we use a smaller telescope, the PSF is bigger, broader, well known. In any case, you will not be able to see anymore that there were two stars, because the image is too large for each star, so they overlap, meaning you have lost the high spatial frequencies by using a smaller ones. And another way of course, to express that would be in this way, to say I know what the point spread function is. I know what how a single a point source, what is this produced. So, let's say I know the PSF of my source, and I convolve the PSF with the image. And this is of course interesting because, in reality we're not just looking at the single star, we may be looking at the galaxy or star cluster. And what we know if we would know what the star cluster looks like, well, we can do some simulations, right? We simulate a star cluster by single particles in some hydrodynamic simulation, and then it's only infinitesimally small points. So we convolve it with the PSF that we know our telescope produce, and then we get some images that look like real observed images.
So the PSF will also depend on wavelength. But how? In this scheme, this is an idea of for where wavelength enters.
Well, I'll get back to the empirical description, but you want more the theoretical argument. I think the theoretical argument is that, of course, size is relative. Right? The size, what does it mean that it's 20 meters? You have to put it in relation with the wavelengths that you look at. Say, in this case, if you look at say at infrared light at 2 micrometers, and you have a 2-meter telescope, then the telescope is 1,000,000 times longer than the wavelengths. Now, if you look at blue light, green light or so, let's say that it's 4 million times bigger than the wavelengths. And so the PSF will be 4 times smaller. Okay. Okay, so this was the background about Fourier transforming. We'll come back in various ways. But I hope this was sort of. Yes.
This system applies to the binary systems, binary stars, applied to systems.
Okay. Well, I've drawn a binary star here, which is invisible from here. So. Yeah, sure. The binary stars is the simple. So those are supposed to be 2 stars. I'm sorry. Yeah. It's a good example for glancing incidents. You will not be able to see it because all the light is yes. So the binary stars, of course, they're very close together, and then that means you have very high frequencies for the space to see them, which means you would have a big telescope. If you have a small telescope, you cannot resolve the binary stars. If you have a big telescope, you can resolve them.
But the convolution is not going to ensure that you recover the original image. If you instead of 2 stars have 3, having the peak and doing the convolution is not going to make you sure that you get 2 stars instead of 3. You get what I mean? When you lose information, you already lose it. And with the convolution, it's not going to make sure that you recover all the original image of the switch.
And within limits, if you have a noise-free image, well, okay. Deconvolution is a tricky business. Fully agree. The problem is that this works mathematically. And you remember that all these transforms go, say, from -infinity to +infinity. A but there is no detector that has an infinite number of pixels. Right? So you already cut your frequencies simply because you have a finite detector for it. Then you have noise, and I think that the deconvolution works to the fourth power of the noise, signal to noise or something. So no matter what, if you add some noise, then there is a limitation. Yes, but it's an art. So, but I think the people after Hubble Space Telescope, there were a couple of people who really understood the convolution and applied it. In radio astronomy, for example, this is cleaning beam. The beam clean procedure is a common procedure because many radio telescopes have very ugly PSS, these interferometers, VLA and so on. I mean, no point source looks like a point or a round figure. It has all kinds of weird structure, but you know exactly what that structure looks like, and you can use that relation to deconvolve it and get your source function from that. But it requires high signal flows. Which brings us to the next topic. So I thought we should say a few words about the sampling. Sampling of a signal. So sampling generally means that you're reading off the value of a signal at discrete values. And that's only given by practicality. There is no system that gives you a perfect recording of measurements continuous in time. You can think of this if you have if you record the signal, you measure the voltage. Yeah? So you measure it now, you measure it again, you measure it a bit later, but there's some time in between. Right? You don't have an instantaneous measurement continuously. You could also say you do the same spatially, detector pixels, or say photographic plates, if you still remember what this is. Have you ever seen photos, real photographic film, rather than just CCDs? Yeah? So, well, you've brought photographic films. Okay. I mean, but even that has some. I mean, there are these silver granules and that have to be developed in the film. Like, you can also say this is sampling, right? Because your photographic film would not be sensitive everywhere, but it's limited to the internal structure where these photosensitive molecules are and those complexes of them. And so they only take certain parts of a continuous image, let's say, or a detector that has some pixels, maybe with gaps in between. I don't know. In any case, let's say we sample a signal and we do it at a discrete frequency, like within this delta function. We can, with delta functions, sorry, with a series of delta functions, we can construct what's called a Dirac comb, right? Comb. That's how it looks. And then this is just the representation here. But the point is that this function here, so what we measure is actually the product of the original function times our sampling function. And the sampling function here, if it's delta functions, that we can calculate using Fourier series. And well, we get back to the Fourier aspect later, but let's say this is our function here. We know that this is how it should look like. Let's say x could be the time, could be something you turn on something, and this is how the values change. Okay, but you don't actually know that because we measure only at discrete times. So what you then measure is given here. You measure it at that point, you get that value corresponding to here. You measure at that point, that should be here, you get that value. right? At this point, small, and so on. See how it works. This is the information that you measure. And then you want to reconstruct the signal, and you may lose some information. And the information, of course, you get the basic structure. I mean, what you then do, of course, when you construct the signals, essentially you connect those, right? But the connection of those points may be different a bit from the original function. Because, as you can see, there is a little wiggle here that will be lost. You will never be able, from your instrument, to tell that there was something there. In other words, and talking in frequency space, there is a frequency here, a high frequency feature, that is above our sampling frequency, and therefore we lose that information. So in that sense, it's again like a convolution of these two functions. And there is an important theory, often used in a very oversimplified version, and maybe I'm oversimplifying here too, but it's called the Nyquist-Shannon theory, which describes the so-called critical sampling. I'll get back to that. Consider a function, f of x, as a Fourier pair, capital F of s, and then sample it, right? This is our function, this is our sampling function, like before, the little arrows, theoretical, whatever. And what we measure is g of x. And so, okay, in this case, again, the solid line here is the function that we measure. The vertical lines here is our sampling frequency, or given sampling frequency you can see here. So we have a sampling rate here with delta x, right? If x is this unit here, again x could be space or it could be time. And we have a sampling rate here of delta x is 1 over 2 Sm. And Sm is given by the boundaries of our function. And then the Nyquist-Shannon theorem says that it's if you have such a function, you can reconstruct f of x here. You can reconstruct features in f of x at a rate of 1 over 2 times the width of the narrowest features. Okay. Now, in other words, what this means is that obviously what you can see here is that, like in the previous example, here we sample this function here with the vertical lines, and these are then the values that we measure. Okay? And in other words, if we connect those points here to measure those values, we will get this function. We will see this. However, what we're completely losing is that spike here, that peak. Right? We have a sampling rate delta x that's at least twice the width of the narrowest feature, whereas this feature is much narrower. So it will not be, you lose the information on that. Okay, and that's the background when you hear people talk about Nyquist sampling. And now I'm doing this oversimplification that everyone does. Let's say this is our PSF. Of course, we know it's much more complicated than this, but let's say this is the central peak of the point spread function. And let's just look at the central part. What's the grid here? These are our detectors. So we just say we look at the point spread function from the telescope and we image it onto our detector. And so this could be our CCD camera, and these little squares here are different pixels. And that means that you should spread your point spread function. Well, you can do that by you design the optical system of your camera, right? So you have a control over the magnification, and so by putting in the right lenses, essentially, you make sure how you can control how big that point spread function is in comparison to your detector pixels. And for a critical sample PSF, so critically sampled means that's following the Nyquist channel theorem. Your PSF covers central full width half maximum of your central peak of the PSF, covers essentially 2 pixels. If it does more, it's called oversampling. If it does less, it's called undersampling. And in this case, you will lose information. In this case, you will just waste detector pixels. So what many people try to do is to make sure that the optics of the instrument is such that the point image with your telescope system and the camera will cover 2 pixels in 1 dimension. And that goes back to this channel 9 sampling here. Here is another example here. Right, these are your points here of the function. So in this case, you would oversample, right, because you have many more pixels. In this case, you lose information on the shape. So matching it is very tricky. Again, in this case, you lose information here. If you make the optics such that your PSF is too large, then that just means detectors are expensive. Right? Good detector costs whatever, a few $100,000, and so you don't want to, for astronomical applications, I mean the ones that are really sensitive and low noise, so you don't want to waste detector pixels. Yes?
How do you determine the boundaries of the PSF? Just that for the, like, even for the mathematical transform, you see the...
Usually it's easier. Well, again, the images you've seen before were in log scale, so it was not so obvious. But if you had, I mean, if we look at the PSF, that's how it looks, right? So, our half maximum is here. This is the size that you want to measure the 2 pixels. Okay? So that factor, something like that.
I have done that in a practical way, and it turns out that the best sampling is not the Nyquist, but about twice the Nyquist. Let's say you have 2 squares there, and here you have 4. Well, the best option, the best compromise is about 3 squares. It's not the Nyquist.
It's
It's like
that's a bit bigger. Yeah, I agree with that. But then I have a hard time to justify why.
Yeah. Well, from the point of view.
Yeah. It's all, yeah. It's sometimes it's also a trade-off between what you want to know about the feature and sensitivity. Because what we say here is of course also not just true for our point spread function, it's also true if you have a spectrograph and you produce a spectrum. Right? Spectrograph will give you some kind of spectrum. And so the line width is the same as here. You want, in order to analyze the spectral information, you also want to have a line width covered by at least 2 pixels. And of course you learn more about the line shape if you have more and so on. But
before noise. So I want to understand into account when I am building that telescope. So in order to have this kind of oversample or typical sample, I need to.
This is mostly for the instrument. If you have the telescope, you don't need to care about it because you don't determine the sampling. Unless you build a really useless telescope where the image is so tiny that no detector would ever be able to resolve it, right? But that's not happening.
No, I was thinking about the fact that having an already choose detector and already choose aperture, there is an optical way to change the size of the spread function with respect to the size.
But that's the task of the optical designer for the instrument.
But there is an optical way.
Yes, okay.
There is something else that perhaps you mentioned, is that a few decades ago there was a fast Fourier transform that revolutionized. Perhaps you should say something.
Now? I don't know. Up to you. Let's do it Thursday. Use that, then I can maybe finish the Thursday. Or if you know about it, you come through.
Yeah, but they don't.
Let's do it Thursday. So here's so far all we did was there was no noise. And the noise is unfortunately one of the biggest enemy of astronomers. First of all, what is noise? Well, so if you don't know, look up Wikipedia, it tells you that it means unwanted sound, or in signal processing, that's what we do in astronomy, right? Processing images or spectra, random unwanted data without meaning. Okay, or irrelevant information. And the signal to noise ratio, that will tell us, that's the relation between useful to irrelevant information. And since the noise is always present, if you describe any discovery of any feature, whether it's an important spectral line, whether it's a small smudge that shows there is an exoplanet or whatever, people will only believe you if you say this has been detected at whatever signal it is. Because if it's, and I'm showing you why this is important. This is an image of a typical image of the scuba is a millimeter instrument on the JCMT, the James Clerk Maxwell Telescope, which is on Mauna Kea, on Hawaii. And it operates at rather very long wavelengths, 850 micrometers. So it will, although it's a large telescope, it will not provide very sharp images. But then, as you already know from Raphael's talk and from Elena's talk, of course there's a lot of re-radiation. The light of the stars gets absorbed by the dust, and then the dust gets heated. And a lot of the radiation, the thermal radiation of the dust, at least on galactic scales, comes out at very long wavelengths. And SCUBA, this is a millimeter instrument, is able to detect those wavelengths. And then you add redshift, right? We look here at the Hubble deep field, which is a very interesting cosmological field. So at a redshift of 3 or 4, the wavelength gets then essentially 3 or 4 times larger, or 4 or 5 times larger. And so this is the image. This is the image of the Hubble deep field seen at 850 kilometers. I'm not sure. It's a good question. I'm not sure whether that's the whole Hubble deep field.
That's really small. Yeah, absolutely.
I would have to look it up. But we can now actually quote what is a galaxy and what is noise. I mean, if your supervisor gives you that image and says you have to write a paper on the galaxies that have been detected in this millimeter, Well, I think we can agree that this is probably a real source, right? This one too, probably. This one, but then it gets difficult. These, nah, certainly not. Right? I mean, where do you draw the line where you say this is reliable information, this is noise? The same is for spectra. This is a spectrum taken with the Hubble with the Spitzer Space Telescope spectrograph. For people who've been here for Raphael's talk, so we saw some of these lines already. So these are, what is labeled here are features, are known spectral lines. But there are many more lines in between, which are not known or expected. So these features here are essentially noise. And so, if you can hardly say, let's see, okay, you want to make an analysis of molecular hydrogen. Okay, it's there, something like that. Of course, you can always measure it here, but it's meaningless because this is just a peak like that one or that one or that one, so it probably does not have any information. So don't just measure something, make sure you know how it compares to the text. Now I wanted to add, since I have shown you the spectrum here, I wanted to add some application of the Fourier transform that we discussed earlier. This is, let's say, okay, this is the spectrum here, or frequency, a signal. And so the intensity is here, and the frequency is here, and you can't see anything because it's very noisy. And then you essentially, in this case it's the power spectrum, but for simplicity, let's just say, understand the basics, it's fine to say, we do a Fourier transform here. Essentially, it's just the square of the Fourier transform. So it tells us at what spatial frequencies is the most power. This is like my example before of the forest, the trees, right? It shows you have many trees here, and then you do the Fourier transform, and you look at what frequency are most of the distance, at what separation are most of the trees. So then, okay, it's hard to see here. So this picture here simply is a zoom in into this bottom part. And then you can see that there is a strong signal here and here, meaning that at low spatial frequency there must be some signal. But of course there are also higher frequencies and higher frequencies and higher frequencies, and it gets up, but you could also guess that this up here is only noise. This is just random. Any random signal will have lots of high spatial and high temporal frequencies. So you say, I cut it off here. I have this function here that's computed by a Fourier transform, and I'll just say I multiply all these high frequencies with 0. So they will be gone in Fourier space. And then I transform it back. And this is what I get. So this is exactly the same as here, but now I have filtered out the high frequencies, which I think are mostly noise. Okay, so I filtered out by using a Fourier filter. I filtered out the high frequency noise, and what I get then is this function here. And again, this could be temporal or spatial, but the point is, I now see something that was completely buried under the noise here, and that I can now see, and this is probably a very, very solid result. So this was just an, yeah.
Perhaps observer because if you cut the frequencies like that, you will find green. The filter has to be a smooth. So they mentioned that the filter to avoid the kind of has to be a smooth. I mean, perhaps the point is that perhaps you make it too simple, but it's a little bit complicated.
Yeah.
It's not that simple.
That's, I couldn't agree more, but given that I put it in parentheses,
It's important to point out that it's not that simple.
yes, there are many more aspects we need to. It's always, I mean, it's a mathematical method that you really need to understand what it does. If you do this for the first time, you apply a filter, and you find something, don't believe it. Right? So you really have to be very careful how you do it and what you do it, and talk to people who've done it before. But this was just an illustration of how useful Fourier transforms can be. Okay, now for the remaining 15 minutes, let's just briefly talk about some of the basics of the, which we actually have, of the noise here. Okay, noise can be distributed in many ways, but there are two distributions that are very fundamental to astronomical data. And one is Gaussian noise. So, of course, you've seen Gauss function before, and Gaussian noise simply means that the noise is distributed according to this Gauss function here. Now, an example here is if you take a nice flat detector and read it, of course, not all the pixels, say you take it in the dark, so you have no signal on it, but you will get values from the individual pixels. They're all around a mean value, right? The mean value here probably corresponds to something like dark red. But there is some scatter here, right? Some pixels, like the yellow ones, are above this mean value. Some of the darker pixels are below this mean value. And the distribution of that, if you would just plot the signal as a function of the pixels, as a histogram, you would get a distribution like that, where this mu is the mean value, right, corresponding to the red color, and the statistics of the characteristics of this Gauss distribution simply are that about 68% of all your data lie within one standard deviation. 95% lie within 95%, and 99.7% are within 3 sigma. So essentially taking the values from here to here. And that's the reason, so that sounds like a big number, and that's usually why astronomers say, well, if the detection is less than 3 sigma, I don't believe it. Okay? And again, it's also a simplified story because it makes a difference whether you have an unknown detection or whether you look for something that you know should be at that wavelength or something. So generally, you want the signal to be 3 times as high as the average noise in your signal. Sorry, you think that.
Sorry? I don't really get what the n exactly is for in this equation, but s divided by n has to be bigger than 3 sigma.
Oh, S stands for signal, N stands for noise.
Okay.
So, and sigma.
That's called the signal over noise ratio. The famous signal over noise ratio.
And sigma is the standard deviation. And so it essentially means your signal has to be 3 times as high as the standard deviation of the noise. Okay? So when I take the metro in the morning, right? When I do that, when I'm on the train in Holland, I usually can't look above people's heads because, on average, yeah, the Dutch people are. I'm rather small, and they're whatever 1 meter 90 or so, right? So the mean of the distribution of the height of people in Holland is say 1.9 meter. But then, of course, you have a certain standard deviation, right? There are, of course, smaller and bigger people. And, well, if you do the same experiment here, then maybe the standard deviation is similar, but the mean value, of course, is, say, I don't know, 170. Okay. There is also the second important distribution, is the Poissonian distribution. And I'm also assuming that you've seen something like that before. But the distribution as described here, shown here. So you have the distribution where lambda is the expected number of occurrences, k is the number of occurrences of an event, so it's the probability, and then distribution is given here. In other words, that was not very well explained. The Poissonian distribution expresses the probability of a number of events occurring in a fixed period of time if these events occur with a known average rate and independently of the time since the last event. Okay, meaning that let's look at the star and we expect a number of photons. We know this, let's not take a variable star, let's just say the star has a constant brightness, or constant luminosity, I should say. And yeah, so we count the number of photons. In the ideal world, we would just get, but of course the arrival time is different. It's a statistical process, and the number of photons is not, it's not, but it's, that would be, of course, then the mean would be lambda. Right? This is, I have the ideal star, and I just count all the events and I divide it by the time. So my mean arrival rate is lambda. But in reality, the star will not send photons, it will send yeah, so there is some change in the arrival times. Of course, if you integrate forever, then it doesn't matter. For short exposures, you may see that in one exposure you have more photons, the star is brighter. The next short exposure, it will be fainter again. And the difference here is given by the Poisson space. So k is actually the number that you actually measure, and lambda is what you would expect, and the difference here follows the Poissonian distribution. The importance is that, like before for the Gaussian distribution where we had a standard deviation, in this case we know the standard deviation is simply the square root of the number of events. And this is very important because if you remember before, when we talk about noise, the standard deviation essentially describes how noisy something is. Right? If the standard deviation is small, it's not noisy. If it's large, then the signal is very uncertain because there are many values, many measurements within around that mean value within one standard deviation. And here we know it's the square root of the number of events. And again, as an example, think about the fluctuations in the detecting photon rate, which of course gives you some background. Then the noise is simply the number of the photons that you've detected. Let's say you had a star, you get some 100 photons or 100 counts on your detector, then you know that according to that statistics that there is an average noise of 10 counts. Meaning that if you do a series of exposures with the same exposure time, then the average is 100 counts, but within one standard deviation, right, you will have sometimes a bit more and sometimes a bit less, and the standard deviation is 10 counts. Meaning that you repeated measurements and sometimes 93 counts and then 109 and whatever. But this gives you an idea about the uncertainty in the signal, and that's it. Okay, and I need to point out that we don't worry, the simple case here, let's not worry about spatial or time average. If we have a perfect detector, that noise between pixels is almost the same as the noise between in time in this case. What I mean with that is this is analogous of, it doesn't really matter whether you have 5 dice, you gamble, right? And then you throw 5 dice and you count the numbers or the eyes on the dice, or whether you do it with 1 and just repeat it 5 times. The statistics essentially is the same. And so whatever we discuss here about time series, again, we have the star that exposes 1 pixel, and then we know the signal on the pixel follows the Poissonian noise distribution. We could also say, well, we have a uniform illumination of the detector, and we expect simply from that Poissonian statistics that some pixels of the detector see more photons than others, simply because of that photon. I think leave it at this, and for the remaining 5 minutes that we have, I'd just like to say one word about the famous signal to noise with respect to instrument sensitivity. Because in the end, of course, this is all, you want to find something, right? You want to discover something. The first galaxy or
Be famous.
sorry?
You want to be famous.
You want to become famous, right? And so you need to discover something, and you will not become famous if you discover the moon because you know it's there. So you need to discover something new, and it's new because people haven't seen it before, and it's probably not so easy to find it, right? So then the question always is, when you build a new instrument or build a new telescope, what can you see with it? You need to estimate the sensitivity, and that means essentially that you need to put in all the noise sources. This is just what we think. This is rather what we've already covered. It's S2N, signal to noise. And the signal, of course, that you would measure, exposure is, what you measure is always the signal plus some background. Remember our first lecture yesterday, where we said the background could be some fluorescent emission from the atmosphere, or the thermal emission from the atmosphere, or some background. You can maybe subtract that, but you have a noisy signal and you have to divide it by that noise. And the noise may have many, many components. If they're statistically independent, you can just add them in quadrature. In any case, your signal to noise what is defined here. And it's improving. I know it's getting late, but maybe one of the most important points to come now. And let's get back to the photon shock loss that we just talked about for the Poisson distribution. And let's just say we have a certain signal to noise detected at some significance. And now it's the same. We just take a longer integration. So we integrate not t, doesn't matter, say here it's 10 seconds. In this case, we integrate 10 times longer. Okay, so we integrate for 100 seconds. So then, if it's 10 times longer, we will of course get 10 times the signal, and we will also get 10 times some background, whatever that is. But since we know from the previous one, from the statistics here, right? Remember that if it's Poissonian distributed, the standard deviation is the noise is the square root of the noise. So the noise increases as the square root of n times the background. So the noise is the square root of the background, of course, so that that the resulting signal to noise is square root of n times what we had before. So if we integrate, say 10 times longer, our signal to noise will not be 10 times better. It only grows as the square root of the integration term. So in that case, it will be square root of n times better. Now that's unfortunate, of course, if you're an observer, right? Because you go there and find something very noisy, and you think it's, well, I just have to expose a bit longer. But if you want to increase your signal to noise, say by a factor of 10, that means you have to integrate 100 times longer. And if you had 1 hour before and you get some noisy spectrum, then you have to integrate 100 times, right? That's whatever 10 nights or so. And yeah, that makes it difficult because half of your nights will be clouded out anyway. Okay, and I think we'll stop there and briefly refer to the rest next time. So, okay. I think it's better.
But this is like, this is the test, right? Bueno, recuerden que mañana no tenemos clase, o sea, es un día de descanso. Bueno, los estudios similares. Piensen en estudiar ciencia como jugar fútbol. Uno la pasa todo el tiempo haciendo cosas relativamente aburridas porque